Welcome to another video explaining the universe using the particle model. Well, this is the second video in a series where I talk about words and phrases, and today I'm going to be talking about constants, in particular man-made constants. Last time I talked about laws of nature, and this time we're talking about constants, man-made. Next time we're going to talk about an interesting constant, C. And last time we talked about how a gentleman said in a talk one time that light obeys wave theory. That was from last time. And today we're going to conclude with a statement by Dr. Glenn Borkett, who talks about the only true constants. Well, we're going to emphasize Newton's universal gravitational constant. And yes, this is the value. This is the value I got out of my physics book. And Newton didn't have a constant, by the way, but he had a statement of proportionality, which stated something like the acceleration of an object between two objects is proportional to the product of the masses and inversely proportional to the square of the distance. And if you're going to make an equation out of that, you have to plug in a constant of proportionality. Scientists and engineers need equations. We like math, and math is a very useful tool. Used it all the time when I was designing, but we need to know how to use math, and we can get ourselves into trouble by taking math too far. Well, the constant itself wasn't determined until 1797-98 by Henry Cavendish, who did this experiment where he measured the rate of acceleration between these two the ball, the small ball and the large ball. He did it by extending light on a mirror and measuring that deflection over time. The interesting point here is that you had to have this balanced. So the bar itself is balanced, the two masses are balanced, and the other bar, it's balanced, and the mass is balanced. And the whole point of that is that it defeats vertical gravity. We're doing a gravity measurement, and this setup sets it up so that there is the effect of vertical gravity is not evident. In terms of the particle model, what is being actually measured here is horizontal gravity. That is the G1 particles coming at these objects, the four masses, in a horizontal direction. Don't often talk about horizontal gravity, but the effect of horizontal gravity is there. And so there's an equation developed. Couldn't find the one that Henry Cavendish used. I think this has been developed since then. If you just rewrite his equation of proportionality and plug in G where it belongs and rearrange, you can solve for it like this. How the people got to this, the bottom is 4 pi r is really the volume of a sphere, and rho e is the density. So this is the mass. And I don't know how 3G got in there, but when Henry Cavendish did it, he got 6.74. Very close, but not today's value. Yes, and I was going to talk about the horizontal force, which I already jumped ahead and have done. Well, the whole question is G a constant? I mean, is it a universal gravitational constant? And the first thing you notice about the current value of G is that it has a plus or minus. Plus, it has this strange unit, Newton meter squared per kilogram squared. We engineers and scientists just plug it in, we just give it that name so that when you put this value of G in that equation for acceleration equals G times m over r squared, all the units come out. What is that? Can you actually describe what a Newton meter squared per kilogram squared is? It's just a hodgepodge to make units work out. We like to make all the units have to cancel out or whatever. But when it comes to constants, you get a mess. Most people would argue that this is probably just accuracy. So this is 6.675 or 6.665 in that range, and that's as accurate as we can get it. And yes, measurement accuracy is important. Talk about that a little bit next time. Now, in my opinion, in theory, if G is a constant, if Newton's statement is precise, that's one question. If it has to be a precise statement, if this G is to be an absolutely a true constant. Well, there was a paper written by Melbourne G. Evans submitted back January 6th of 1958 at the University of New Mexico. Excellent paper. I actually went online and bought a copy of this paper. And he makes some, in the paper, Evans goes through and researches very carefully and finds statements that Newton had made in various places, which relate to how precise is Newton's equation, what was his opinion of it, if you will. So in one part of the paper, Newton adds, there it is. Newton adds, you could find gravity. You find that gravity decreases and can be no other than from the superficies, the surfaces of the planet, then reciprocally duplicate of the distance from the center. But downwards, that proportion does not hold. So he's saying it's from the surface up, it's good, but downward not. Up is kind of an interesting point that he's making because most of his gravity, his statement of proportionality comes from a lot of Kepler's work and Tycho Brahe, his work, and all of that was done with planets and distant stars that were far away, distant, almost to the point where they're points themselves, and so you could treat a galaxy in the distance as a point. And it works out in that direction. But down below, he wasn't sure because you don't have the same geometry going for you. So he didn't think it held below the surface of the Earth. Later in the paper, after I found that the force of gravity towards the whole planet did arise from and was compounded of the forces of gravity towards all its parts, and towards every one part was in the inverse portion of the squares of the distance from the part, he was still in doubt. In other words, he took the Earth and he broke it up in pieces and kind of thought through the process of how one part of the Earth interacts with another part and goes around it. But he still had doubt. He had doubt whether that portion inversely as a square of the distance did accurately hold. In other words, he didn't think it was still not precise, although he had some feeling it might, or but nearly so. In the total force compounded of so many partial ones, For it might be that the proportion which accurately enough took place in greater distances should be wide of the truth near the surface of the planet, where the distances of the particles are unequal and their situation is dissimilar. And if I remember the paper, I don't have it quoted here, he was really talking about, for example, the tree, the apple, and the earth. Those aren't point masses anymore. And so he didn't think it even worked on the surface of the earth. So Newton himself had concern about how precise his equation was. Well, I'm going to go back to a time when I was first introduced to this whole science idea and gravity. When my son David asked me to help with an experiment, uh, did an experiment that was developed by Dr. Karazani, that was going to prove that Lesage's gravity was, in fact, the right gravity, and the normal gravity that Newton talked about was not. This is an actual drawing from a paper I wrote after we did the experiment, and there's a twist. This is like Cavendish, only there's a twist to it in the fact that instead of one small ball and one larger ball, if you will, he suggested four blocks, three blocks, excuse me, and one ball. And the idea was that this, if Newton was right, this ball ought to move towards the larger mass. Weak force this way, strong force that way. If Lesage was right, then what Lesage called as gravitons would push the ball towards the small one. So you could see it. Obviously, ball goes one way, then the other way. Which way was it going to go? Well, the very first thing I did was I decided to develop an equation using Lesage. Then I used Newton's equation, and I did take care of mass distribution. I broke this up in four pieces, and calculated the force on this object when it was in the middle, force to all 12 points, and then if it was way over here or here, I calculated the force, developed a force curve. Did the same thing with Lesage, where I have G1 particles coming in here, and I lose some here, and I lose some here. In this particular case, they look like it would have been balanced, and the net force would have been, the net force towards here or the net force this way would be equal. Did the calculation and plotted the curves. These are the two equations. This is Newton's equation for force, and there's G as a constant, and there's R squared. This is my equation for a particle gravity, if you will, or a Lesage's type gravity. Lesage, as far as I know, didn't develop an equation. I'm not going to explain this to you, but only to point out that there's the constant G, and you don't see any constants here, although there's one buried in these percentage terms. There's the interaction factor buried in there, and then there's another constant which is not part of the equation, but it turns out that the number of paths, which this tells you how many paths, and this is the force per path. You multiply the force per path times the number of paths to get another constant. There are constants here, but it's not explicit. Point being, these are totally different equations. One based on Newton's statement of proportionality plus the constant, and clearly R squared. R squared doesn't appear in my equation explicitly. It is in the geometry, but not in the equation. And this was my result. This is I did a three-dimensional calculation, not just two. I did a three-dimensional calculation, and I plotted the two curves. The dark one, the black one is the push, and the red one is a pull. You can see right away, before I even did the experiment, the ball was going to go the same way. It wasn't going to go in opposite directions. In the experiment, we had to do it accurately enough to compare the measured value to this curve or this curve. Doomed to failure. It was amazing. We even went through it. So anyway, by the way, that curve, let me go back. That curve, after we did the experiment, we wrote a paper, went to a conference in 2007. When we got back, or on our way back, I was talking to David, and I said, well, Dave, I guess I'm done. I don't have anything to do. Well, I guess because at that point I had no idea what I would do. Well, it didn't take me more than a couple of weeks, and I was thinking about these curves, and I'm asking, why in the world are these two curves the same when the equations are so different? I got hooked. That was in 2007. I got hooked, and I haven't stopped since. Okay, and so let's talk about whether these equations are precise. Newton said no, he wasn't convinced that it was precise, and in particular, when he comments about the tree, the apple, and the earth, he's talking about mass distribution. He didn't say that. I'm putting words here in Newton's text, if you will, but it doesn't account. Everybody assumes, as Newton stated, that you take the mass of the apple and you shrink it down to a point. You take the mass of the tree, you shrink it down to a point, and the earth, and then you use the equation. That's a big assumption, ignoring the mass distribution, because gravity has to work on the whole object. It can't work just on the center of it. It would have to calculate. Gravity would have to calculate where the center was and then use Newton's equation. Well, that doesn't happen. Well, my equation? Well, my equation, it's not precise either. Let's face it. My equation accounts for mass distribution because when I calculate the loss as the G1 particle goes through various parts, I have to calculate the amount of mass it's passing through, and assign it a loss based on that mass. And I eventually account for the mass of the whole thing, of that experiment, and how it's distributed. And so it does account for it. It accounts for the mass distribution of the Earth and the Moon, for example, if I were to apply to that. But the equation assumes that the Earth and Moon are perfect spheres and homogeneous. Another assumption, it tends to make my equation more accurate because the equation forces you to take account of mass distribution, but it doesn't tell you it can't be a perfect sphere. However, you could say, okay, I'm going to have an oblate spheroid instead of a perfect sphere. Could do that. Or you could assume there's an atmosphere around it. You put an atmosphere around it, and then the Earth as an oblate spheroid. You can account for the mass distribution as much as you want. And when you do that, the equation forces you to account for that. Makes it more precise, but still, they're all estimates. There's the equation, my equation, Newton's equation, not precise. My conclusion, maybe didn't get there exactly right, but nature doesn't need constants to do what we see it doing. Man needs constants to change the statements of proportionality into equations. You got all kinds of other constants, Planck's constant, Boltzmann's constant, and on and on. I mean, you go out and see the whole list of man-made constants, and all are based on equations, and all the equations are make big assumptions and therefore not precise. Now, until the equations are precise and includes all the necessary terms and exact details of geometry, can be no true constants. Well, that led me to try to get out of this the sense of how am I going to say I got two constants in my equation when I know they can't be true constants? I've come up with my own term called the virtual constant. So I looked up virtual on the internet. For example, describing a company as a virtual monopoly. Monopoly. This is an example of, we often hear these phrases. Virtual means it's pretty much a monopoly, but not technically one, perhaps because of a few minor competitors. My definition of virtual constant means it may work in a limited context or in a region, but it may not work in all cases. I could determine through using Majorana's experiment, and I have done this, those two virtual constants of my equation. And but it's all been tested on the surface of the Earth. What about at the edge of the galaxy? Do my constants hold there? Guess what? I already know they don't. They don't hold out there at the edge of the galaxy, even though I can calculate them here. So there are virtual constants. Depends on where you are, what your situation is around you. Uh, Glenn Borker talks about the unicosm, the place where you are, or where your experiment is. And then there's a microcosm, everything going on below that you don't even account for, and the macrocosm above you, around you, that you don't account for. Um, you know, if you don't account for everything, it can't be precise. These are just virtual constants, and you've got to readjust things when you get to a new situation. Well, Dr. Karazani, in the back of his book, Storm in Physics is the title of his book. David helped get that published for him. In the back, he has a statement I really like. I like this statement. It sounds funny because he's Argentinian, but he states, nature will never follow a mathematical invented equation by humans. Remember last time I said this guy said light obeys wave theory. No, nature will never follow these equations. They're out there doing their own thing. And here's Glenn Borker's statement about constants. The only true constants are 0 and 1. And his point is 0 means nothing, empty, zilch, nada, 1 meaning everything. He claims that all the rest of them are not really constants. And that's what my whole point here today is. Constants of proportionality that we talk about as constants can't be unless the equation is precise. My name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask Particle. Thank you for your attention.